Okay, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Okay, for this course, SMQ3043 Linear Programming, there are 5 chapters. The first one, Basic Linear Algebra, that you have learned in the previous semester. And then second chapter, Introduction to Linear Programming. Third chapter, the Simplex Algorithm. And then followed by sensitivity analysis in chapter 4, and the last one is transportation problem. Okay, so for this course you can refer to several textbooks such as Hillier 2015, and then Taha 2017, and also Winston 2004. Alright, so chapter 2, Introduction to Linear Programming. Basically, this chapter describes the general characteristics shared by all linear programming LP problems and the steps to formulate the problems. It is then followed by the graphical method for LP problems involving two variables. And then the remainder of the chapter explains how to formulate and solve LP problems of some real-life situations such as a production problem, diet problem, and solving these simple LPs will give us useful insights for solving more complex LPs. LP was first studied during World War II when there was an urgent need to allocate scarce resources to the various military operational problems in an effective manner. Since then, LP has evolved and become an important tool for solving many operation research problems. It has been used to solve optimization problems in industries as diverse as banking, education, forestry, petroleum, and trucking. So I give you about 2 or 3 minutes. Try to Google what is operations research and also linear programming.
Assalamualaikum and good day. This video will introduce you to a linear programming problem and how to formulate an LP model. A linear programming is an optimization technique for a system of linear constraints and a linear objective function. Linear programming is useful for many problems that require an optimization of resources. It could be applied to manufacturing, to calculate how to assign labor and machinery to minimize cost of operations. It also helps to decide which products to sell and in what quantity in order to maximize profit. The objective of an LP problem is to maximize or minimize some quantity. An objective function defines the quantity to be optimized, for example, to maximize profit or to minimize costs. And the goal of linear programming is to find the values of the variables that maximize or minimize the objective function. All LP problems have constraints that limit the degree to which the objective can be pursued. If both the objective function and the constraints are linear, the problem is referred to as a linear programming problem. Linear functions are functions in which each variable appears in a separate term raised to the first power and is multiplied by a constant, which could be 0. This function is a linear function because both variables are separate are in different terms, while this function is not a linear because the power of x is 2. This is a quadratic function. This equation is not a linear function because there exist two variables in a single term. Earlier, linear constraints are linear functions that are restricted to be less than or equal to, greater than or equal to a constant. A graphical solution method can be used to solve a linear program with two variables. A constraint is an inequality that defines how the values of the variables in a problem are limited. In order for linear programming techniques to work, all constraints should be linear inequalities. The feasible or possible solution of the LP problem only satisfy all the problem's constraints. Therefore, we need to find the best solution of the problem. The optimal solution or the best solution of the problem is a feasible solution that results in the largest possible objective function value when maximizing, or giving smallest objective value when minimizing. These are the guidelines for model formulation. First, you need to understand the problem thoroughly. Then, define the decision variables. Next, write the objective functions and the constraints. These functions need to be written in terms of decision variables. And finally, identify any upper or lower bounds on the decision variables. This is the general form of an LP problems. The first line is the objective function, either maximize or minimize z. We can see here x1, x2 until xn represent decision variables. Subject to a group of constraints. The number of constraints depends on the problem. The constraint can be either an equation or inequality. The last line is the boundary of every decision variable. Now let's discuss example 2.1. Kinderwood Sdn Bhd manufactures two types of wooden toys, trucks and cars. A truck sells for 27 ringgit and uses 10 ringgit worth of raw materials. Each truck that is manufactured increases Kinderwood's variable labor and overhead costs by 14 ringgit. A car sells for 21 ringgit and uses 9 ringgit worth of raw materials. Each car built increases Kinderwood's variable labor and overhead costs by 10 ringgit. The manufacture of wooden trucks and cars requires two types of skilled labor, carpentry and painting. A truck requires 2 hours of painting labor and 1 hour of carpentry labor. A car requires 1 hour of painting and 1 hour of carpentry labor. Each week, Kinderwood can obtain all the needed raw material but only 100 painting hours and 80 carpentry hours. The demands for cars is unlimited, but at most 40 trucks are bought each week. Kinderwoods want to maximize weekly profit. Formulate a mathematical model of Kinderwood's situation that can be used to maximize Kinderwood's weekly profit. To formulate the model, we need to define the decision variables. In this problem, Kinderwood wants to maximize its weekly profit, and the profit comes from the wooden trucks and wooden car. Therefore, Kinderwood must decide how many trucks and cars should be manufactured each week. Here, two decision variables involved in this problem, which is x1 represents the number of trucks produced each week and x2 represents the number of cars produced each week. Before we go to the next step, we need to extract the information from the problem. Write all information points in a table so that it's easy for us to construct the objective function and constraints. We have two columns, x1 and x2. Let's read the problem sentence by sentence. A truck sells for 27 ringgit and uses 10 ringgit worth of raw material. 27 ringgit is the price of a unit of wooden truck, and 10 ringgit is the cost of raw material. So we have a row for price and write 27 ringgit under x1. We also have a row for raw materials and write 10 ringgit in column x1. Now, from the next sentence, we know that the labor and overhead cost to produce a unit of wooden truck is 14 ringgit. So we have a row for other costs. And write 14 ringgit in this cell. Next, each car sells for 21 ringgit, use 9 ringgit of raw materials, and variable labor and overhead costs by 10 ringgit. We fill in this information in column x2. The manufacturing of these toys involve carpentry and painting process. 2 hours of painting and 1 hour of carpentry are needed to produce a unit of truck. While a car requires 1 hour of painting and 1 hour of carpentry labor. For X, now we have two new rows, painting and carpentry. Two hours under X1 and 1 hour here for carpentry. For X2, we have 1 hour painting and 1 hour carpentry. From this sentence, there is no limit for raw material, but only 100 painting hours and 80 carpentry hours available each week. In column limit, we know that Kinderwood can use not more than 100 hours of painting and maximum 80 hours of carpentry works. Finally, demand for cars is unlimited, but at most 40 trucks are bought each week. This sentence tells us that Kinderwood can produce wooden cars as many as they want, but they can't produce more than 40 trucks every week. We write this information here. Using this table, we can proceed to the next step, which is constructing the objective function. The objective of this problem is to maximize Kinderwood weekly profit. And the profit is equal to weekly revenues minus weekly costs. Let's refer to the table. The weekly revenues or weekly income is 27 ringgit times the number of wooden trucks produced per week plus 21 ringgit times the number of wooden cars produced each week. Thus, weekly revenues is 27x1 plus 21x2. The weekly costs come from the cost of raw materials, labor and overhead costs. We gain the information from these two rows. Weekly raw material cost is 10x1 plus 9x2, and weekly labor and overhead cost is 14x1 plus 10x2. Therefore, weekly production cost is 24x1 plus 19x2. Now, we substitute both equations into the formula to get Kinderwood's weekly profit. Which is, the weekly profit is equal to 3x1 plus 2x2. This is the objective function of Kinderwood's LP model. We move to the next step, which is constructing function. Now, let's move to the next step. which is constructing function of the constraint. The values of x1 and x2 are limited by the following three restrictions. The first constraint is the printing hours. Each week, Kinderwood cannot use more than 100 hours of painting time. Therefore, the function of this constraint is 2x1 plus 1x2 less than or equal to 100. The second constraint is each week not more than 80 hours of carpentry time may be used. Thus, the function is x1 plus x2 less than or equal to 80. The third constraint is the limitation of the wooden trucks production. At most, 40 trucks should be produced each week. Means x1 is less than or equal to 40. Finally, we combine all the functions into one complete model. For the Kinderwood problem, the model is maximize z equals to 3x1 plus 2x2 subject to 2x1 plus x2 less than or equal to 100, x1 plus x2 less than or equal to 80, and x1 less than or equal to 40. And the last line is very important because we need to set the boundary of every decision variables. This is the complete LP model for Kinderwood problem. That's all for now. I will show how to solve two variables LP problem in the next video. Thank you.
Alright, as mentioned before, two important things in this chapter are first, to formulate, and second, to solve LP problems. So, today we have learned how to formulate an LP problem, which is a Kinderwood problem. Please do this exercise, exercise 2.1, a ColourWorld problem, as your homework. Thank you. See you in the next class. Cheers.